Okay, so this video is going to be looking at an example of a bond energy calculation. In this video, I'm going to show you how to do the bond energy calculation. I'm also going to talk around some of the theory behind the bond energy calculation, behind what's going on. So, what have we got? We are dealing with a reaction, a combustion reaction, a burning reaction between methane and oxygen. Okay, so we are burning methane in oxygen. It's the usual sort of gas tap kind of a deal, and we're going to get carbon dioxide and water. We're looking for complete combustion here. In this reaction, as in pretty much all reactions, we're going to have some bonds which get broken. Now, breaking bonds requires energy. Energy goes into the system. That makes it an endothermic process. Okay, and endothermic processes have a positive sign on them because energy is going into the system. In this reaction as well, as again with all reactions, or pretty much all reactions, some bonds, some new bonds are going to be made. Making bonds is an exothermic process. You have an attraction being made. In terms of bonding, that's an electrostatic attraction between oppositely charged species, whatever those oppositely charged species may be in this case, and energy is released. Because energy is released and energy is lost from the system, this portion of the sum will have a negative sign, which is why we have the negative sign before the bonds made part of the sum. So, getting to the sum itself, we have delta H, change in enthalpy. That is the sum, sigma, here the mathematical sign sigma, means the sum of all the bonds broken, so the energies related to all the bonds broken, I'll talk about that in a second, minus the sum of the energy of all the bonds made. Now, the best way to do this sort of sum, and the way it's often laid out in GCSE questions, is to break down the two parts and then put them back together. So we are going to work out first sigma bonds broken, which we really should write out in full in a GCSE. So we're going to write out sigma bonds broken. Now what we've got to see is what sort of bonds are broken. Well, if we look at the left-hand side of our equation, we have some CH bonds. Let's circle one. There's a CH bond there. There's one of them. There's a second one. There's a third one. And there's a fourth one. So we have 4 lots of CH single bonds. And that's important, single bonds. What else do we do? Well, we have, and this is added to, we have an oxygen-oxygen double bond. Now, you'll note down in the data, we have data for an oxygen-oxygen double bond. The oxygen-oxygen double bond is not worth 2 of the oxygen-oxygen single bond for reasons that we won't go into in this video. But if you are interested, it's to do with sigma bonds and pi bonds and the different spatial orientations of those. So go and have a look if you're interested. If you're not, don't worry about it. Just know that a double bond is not twice the value of a single bond. But anyway, where are we at? Well, I've circled one of those oxygen-oxygen double bonds. We actually have 2 of them, so plus 2 times that. Okay, so those are the bonds that we're breaking. We're breaking 4 carbon-hydrogen bonds and 2 oxygen-oxygen double bonds. Right, so we need the values for those. So now we substitute in the values. 4 times 412. Where did I get that from? 412 is the value for a single carbon-hydrogen bond. Quick note here, there's no sign in front of the 412. If we are breaking it, it is effectively going to be a positive sign. If we are making it, it is going to be a negative sign. But as I said earlier, that negative sign is dealt for us. The value of a bond is the same whether you make or break it due to the conservation of energy rules. Okay, what else have we got? We've got 2 lots of the oxygen-oxygen double bond. We've already highlighted that, so we can put that in. 2 lots of 4, 9, 6. And this, when you put it all together, equals 2640. Now, that does have units. It's kilojoules per mole. If this was a partial question where they wanted a final answer, I should put in the units, kilojoules per mole. Right, so that's that bit. Done half of it. Let's tick, done that bit. Now I need to do the sigma bonds made. I'm not going to bother with the sign at the moment. I'm going to put the sign in when I pull the whole thing together. Again, I'm going to write this out in full. Sigma bonds made. You have to do that for the examiner at GCSE. They like to see that. Okay, what have we got? Well, we are now dealing with the stuff on the right hand side, the stuff that has been made, the products. What have we got? Well, we've got a carbon-oxygen double bond. We've got at least one of them. How many of them have we got? One, which I've marked up, and the second one, two. So I've got 2 lots of them. And I have 1, 2, 3, 4 lots of the OH bond. Now, you'll notice in this that I've jumped straight to this display formula equation. Okay, I've jumped straight to that. That is because by looking at this, I can see exactly which bonds I am dealing with. To get there, if you're doing it in full, you have to go via the balanced chemical equation, because you need to be able to get the balancing right. And it's easier to balance one of these most of the time than it is to balance one of these display ones. There is some knowledge that you have to have. You have to have the knowledge that oxygen, the diatomic oxygen, has that double bond in it, has that double bond there. You have to have that knowledge. You have to have the knowledge that carbon dioxide equally has those double bonds in. That is knowledge from the bonding that you would have done in the previous year. Okay, so moving back to my little sum that I've got here. I've got 2 lots of the CO double bond. Now you can see the CO double bond is pretty strong. There's a large magnitude, a big number basically, associated with it. So I've got 2 lots of 7, 4, 3. And I've got 4 lots of the OH bond. Just double check you're happy with that. 4 lots of the OH bond. I've got 2 water molecules, but each water molecule has 2 OH bonds in it. So I have 4 lots of the OH bonds. So that's 4 lots of 4, 6, 3. And if I add all that up, I get 3, 3, 3, 8 kilojoules per mole. Now, mathematically, I can already see that I'm going to be happy with this, because this number, the amount of energy given out, is a bigger number than this number, which is the amount of energy taken in. Which, if I think about it, is where I should be with this, because this is a combustion. This is a Bunsen burner burning. This is stick your hand in it and it's ouchy because it's hot, because heat energy is being given out. So I should have a bigger number being given out for an exothermic reaction than being taken in, because more energy is going to be released making the new bonds than is taken in breaking the old bonds. Let's just work that out in full though. Delta H equals sigma bonds broken. I know this is written at the top. I don't care that this is written at the top, because in an exam it wouldn't be written at the top. And you would need to write it in so the examiner knows what you're using. Delta H equals sigma bonds broken minus sigma bonds made, which is 2,640 minus 3,338, which equals minus 698 kilojoules per mole. So I've got a nice negative number there, which is what I was hoping for, which is what I was expecting. So I have an exothermic reaction, which is good because it's it's a combustion, it should be exothermic. And let's just have a quick recap on why. More energy is released, making new bonds than is taken in to break old bonds. One last thing I do want to say here, you'll notice that I broke all of the bonds on everything on the left, so all of these bonds were broken on the left and all of these bonds on the right were remade. Now, it may be that you come across reactions where some of the bonds appear on both sides. Easiest thing to do, break everything on the left, make everything on the right. If you're breaking and making the same bond, it ends up being zero sum, which is obviously what is actually going on, which makes no difference to the reaction. It's just easier to keep a track. But otherwise, that's how to do that reaction. That's how to do that calculation. Best thing to do now, have a go for yourself and see if you come up with the same answer.